Lie back and let your body sink into your bed. Close your eyes gently and feel the quiet around you. Breathe slowly, in and out, and imagine the world outside fading away. Let your thoughts drift lightly like clouds across a calm sky. Tonight, we will explore a question that stretches across the universe itself, a question that has puzzled scientists, philosophers, and thinkers for decades. If the universe is so vast, and if life has emerged elsewhere, why have we never seen another civilization? Why is the night sky so full of stars and yet so empty of answers? What if every civilization out there is hiding? What if they are quiet, careful, and invisible because the universe is not as safe as it seems? This is the essence of the dark forest theory. It suggests that life may be abundant, but intelligent life may choose to remain silent to survive. This idea begins with the Fermi paradox, named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox arises from the contrast between the high probability of life elsewhere and the lack of evidence for any of it. On one hand, the universe contains billions of galaxies, each with billions of stars, many of which host planets capable of supporting life. On the other hand, despite decades of searching, listening, and observing, we have not detected a single confirmed signal from an alien civilization. The dark forest theory reframes this silence not as absence, but as strategy. Just as animals on Earth hide to avoid predators, intelligent civilizations may remain hidden to avoid contact with unknown threats. In this analogy, the universe is like a forest at night. Every being moves quietly, observes cautiously, and avoids drawing attention. Survival depends on staying unseen. This does not necessarily mean that other civilizations are hostile. It may simply mean that silence is the safest choice when the intentions of others are unknown. A single misstep, a single signal could attract attention from a civilization that acts with different priorities, or worse, with aggression. To understand why this is plausible, we must first consider the vastness of space. Our galaxy, the Milky Way, contains an estimated 100 to 400 billion stars. Many of these stars host planets, and a growing number of exoplanets are being discovered within habitable zones where liquid water could exist. The Kepler Space Telescope and other instruments have shown that planets are common and that Earth-like worlds may be numerous. Beyond our galaxy, billions of other galaxies stretch across the observable universe, each containing its own stars and planets. The sheer scale suggests that life could arise elsewhere many times over. Yet, despite this potential abundance, our sky remains silent. Observing other civilizations is difficult for several reasons. Light and radio waves travel at a finite speed, limiting how far and how fast signals can reach us. Even if a civilization transmits powerful radio messages, they may only reach a small part of the galaxy over thousands of years. Additionally, civilizations may not broadcast signals at all. Human technology emits radio and television waves that gradually fade over distance. Beyond a few light years, they become indistinguishable from background noise. Other civilizations may be far more advanced, using energy-efficient systems that leave no detectable signature. Silence, in this sense, is not only survival, but also a product of technological evolution. The Fermi paradox is more than just a question. It is a framework for thinking about our place in the cosmos. Many possible solutions exist, ranging from the rarity of life to the self-destruction of civilizations. Some suggest that intelligent life may be extremely rare, emerging under very specific conditions. Others propose that civilizations do not last long enough to be detected, either because they exhaust resources, fall victim to natural disasters, or destroy themselves through conflict or environmental collapse. The dark forest theory adds another layer. Even if life is common and civilizations survive, they may choose to remain invisible. The absence of evidence becomes a deliberate feature, not a flaw in observation. The dark forest analogy is powerful because it appeals to behavior observed on Earth. Species that are cautious tend to survive longer, especially in environments where predators or competitors are unknown. A small animal moving quietly through a dense forest avoids attracting the attention of larger predators. Similarly, a civilization that broadcasts its location across interstellar distances may expose itself to risks it cannot anticipate. The unknown scale and diversity of potential threats in the universe makes silence a logical strategy. This pattern of quiet observation may extend across millions of planets, creating a cosmos filled with life that is skillfully hidden. Light from distant stars teaches us about the universe, but not necessarily about life. A star may be surrounded by planets, some of which host complex organisms or even advanced civilizations. But if those civilizations do not emit detectable signals, we have no way of knowing they exist. Our instruments can measure the chemical composition of exoplanet atmospheres, search for signs of water or oxygen, and detect energy usage in certain cases. Yet, the presence of intelligent life may remain invisible because they control their emissions, shield their activity, or operate at scales and wavelengths we cannot yet observe. The universe may be full of civilizations, quietly watching one another while leaving no trace. Time adds another layer of complexity. The universe is over 13 billion years old. Civilizations may have risen and fallen long before humanity appeared. The light from some planets may take millions of years to reach us, and by the time it does, the civilization may no longer exist. Even if two civilizations exist at the same time, they may be separated by thousands of light years, making contact extremely unlikely. This means that silence is not only a choice, but also a natural outcome of the vast distances and differences in timing between civilizations. Survival may favor those who hide, not those who call attention to themselves. Understanding the dark forest theory helps us approach the search for extraterrestrial life with caution and curiosity. It reminds us that the absence of contact does not imply the absence of life. Life may exist, it may be intelligent, and it may have developed technologies far beyond ours. Yet, in a universe filled with unknown risks, the safest choice is often silence. This perspective blends astronomy, biology, and logic, suggesting that careful observation, patience, and humility are necessary when considering life beyond Earth. The universe may be teeming with life, but all of it may be hiding, waiting, listening, and remaining unseen, like shadows in a cosmic forest. The universe stretches farther than the mind can picture. Each night, when we look at the stars, we see only a fraction of what is there. Our galaxy, the Milky Way, alone contains hundreds of billions of stars. Many of these stars have planets circling them, some similar in size and temperature to Earth. Beyond our galaxy, billions of other galaxies drift across the cosmos, each filled with their own countless stars. The numbers are so large that it is almost impossible to grasp. Yet, within all this abundance, signs of other civilizations remain invisible. Even though there are so many worlds, finding life is not simple. Stars are separated by immense distances. Light, which travels at a fixed speed, takes years, centuries, or millennia to cross the space between them. A signal sent from one planet may not reach another for thousands of years. When it finally arrives, the civilization that sent it may no longer exist. Even if intelligent beings are present on many planets, the vast distances make it extremely unlikely that we could detect them at the right time. Our attempts to observe other life rely on careful tools. Telescopes collect light and break it down into signals that reveal the properties of stars and planets. Radio telescopes listen for artificial signals, searching for patterns that might suggest intelligent origin. Instruments like the Kepler Space Telescope have discovered thousands of planets, some within habitable zones where water could exist. Newer telescopes can even measure gases in distant atmospheres, seeking traces that might hint at life. But all these observations face limits. Distance, interference, and faint signals make detection extremely difficult. Most planets remain only points of light or faint shadows against the background of space. Distance also changes the meaning of time. The light we see from a star may have traveled millions of years before reaching Earth. We see that star not as it is today, but as it was in the distant past. The same is true for planets and potential civilizations. Signals we detect might reflect a long-extinct world. Conversely, a planet bustling with life today may be completely hidden from our view. Its light too faint, its signals too weak, or its activities intentionally concealed. Observation is like trying to understand a vast forest by looking through a single, narrow window. Even when we try to detect artificial signals, we face subtle challenges. Radio waves spread out and weaken over distance. They can be absorbed, scattered, or drowned out by cosmic background noise. Civilizations may not broadcast signals at all, preferring to communicate silently or using technologies beyond our current understanding. Our most sensitive instruments, listening day and night, pick up countless natural sources, stars, pulsars, and cosmic events. But few, if any, reveal intelligent origin. The universe may be full of life, yet it remains hidden behind layers of space, time, and natural interference. The rarity of detection is further amplified by timing. A civilization that sends signals for only a few centuries may coincide with ours for a brief moment. Even if thousands of civilizations exist across the galaxy, the chance of overlap in time, distance, and method of communication is small. Silence, then, is not necessarily absence. It can reflect the reality that intelligent life is difficult to observe, even when it is present. The universe continues its vast, quiet dance, with stars burning and planets turning, while most of its inhabitants remain beyond our reach. The scale of the cosmos also forces us to rethink what is visible. Earth itself emits only a faint bubble of radio waves into space, extending a few dozen light-years. A distant observer would need powerful instruments, precise timing, and extraordinary luck to detect our presence. If we struggle to detect ourselves from nearby stars, imagining how to detect other civilizations across thousands or millions of light years becomes even more daunting. Our observational limits shape what we understand about the universe, reminding us that silence does not always equal emptiness. Despite the obstacles, scientific methods continue to advance. Radio telescopes scan the sky systematically, targeting nearby stars, known exoplanets, and regions where conditions for life appear favorable. Optical telescopes study reflected light from distant worlds, measuring atmospheric composition and searching for biosignatures. Gravitational lensing allows glimpses of planets otherwise hidden behind stars. Each technique adds a piece to the puzzle, slowly revealing the possibilities for life, while emphasizing how much remains unseen. Patience and careful measurement are key, because the universe does not offer its secrets quickly. The cosmic scale and rarity of observation shape our understanding of the dark forest theory. Silence may be deliberate, enforced by both risk and distance. Civilizations that wish to survive may choose not to reveal themselves. Even if life is abundant, the sheer vastness and the physical limits of space mean that most of it will remain hidden from us. Listening and observing becomes an exercise in humility, a recognition that the universe is larger, older, and more complex than we can easily perceive. Each faint signal or distant flicker of light is a reminder of the possibilities, yet also a warning of the limits of our reach. The vastness also teaches perspective. Even if we detect signs of life, understanding them may take centuries. Light and signals travel slowly, and civilizations may change, evolve, or vanish, while our instruments are still searching. Observing another world is not merely a question of finding it, but of interpreting a fragment of its existence across time and space. In this immense silence, the dark forest theory gains weight. It suggests that life may be abundant yet cautious, hidden in plain sight behind the curtain of the cosmos. The universe is large, and life may be everywhere, quietly observing, waiting, and remaining invisible. Even with our most advanced instruments, the universe remains mostly unseen. Every star we observe is a point of light, and most planets appear only as tiny shadows or slight wobbles in their star's motion. We can detect some planets because they pass in front of their stars, dimming their light just slightly, but this method works only from certain angles. Other worlds remain completely hidden, and many that are visible may give us no information about whether life exists there. The universe is vast, and our observation methods, however sophisticated, capture only a fraction of what is out there. Beyond the limits of light, there are other forms of radiation and energy we can study. Radio waves, infrared, and even X-rays may reveal signs of activity. Some scientists hope to detect structures or energy use that could only be explained by intelligent civilizations. Yet even this has limitations. Signals fade over distance. A civilization's activity might be too faint, spread out, or deliberately shielded. A galaxy filled with advanced life might appear completely silent, simply because its civilizations choose to stay hidden, or because their emissions are beyond the range of our detection. The scale of space also shapes how we search. Stars are not evenly distributed. Some regions are densely packed, while others are vast voids. Neighboring stars can be light years apart. Even within our own galaxy, sending a signal from one point to another takes decades or centuries, depending on distance. If civilizations rely on subtle methods of communication, or if they only use energy-efficient signals, the chance of detection drops dramatically. Even our own signals, broadcast unintentionally from Earth, extend only a few dozen light years before fading. The universe, though full of life, may remain invisible because the distances themselves act as barriers. Timing is another challenge. A civilization may exist for only a short period in cosmic terms. Humans have been able to send radio signals for just over a century, a fraction of a second in the life of the galaxy. Another civilization may have risen, used communication for a few hundred years, and disappeared long before we developed the ability to detect it. Or it may be just beginning its technological phase, too young for its signals to have reached us. The odds of overlapping perfectly in space and time are extremely small. This temporal gap ensures that even abundant civilizations may never make contact with each other. Observing life on distant planets is also complicated by the interference of natural cosmic phenomena. Stars flare, pulsars emit bursts of energy, and interstellar clouds scatter radiation. Even if a signal is artificial, it must be distinguished from the immense background noise of the universe. This requires long observation times, careful analysis, and advanced algorithms. A brief signal might be overlooked, buried beneath the constant activity of space. Civilizations that wish to remain hidden can exploit this natural noise, blending their existence into the background so effectively that even the most careful observers might fail to notice them. The search for extraterrestrial life has adapted to these challenges with ingenuity. Arrays of radio telescopes scan the sky, listening for narrow, repeating signals that could indicate intelligence. Optical telescopes look for small changes in starlight that suggest planets or megastructures. Scientists have begun to analyze the chemical composition of atmospheres, searching for oxygen, methane, or other molecules associated with life. Even small hints, like an unusual heat signature or a subtle light variation, can raise questions about whether a planet hosts life. Yet, despite these efforts, the universe often offers only silence. Part of this silence may be deliberate. Civilizations that understand the dangers of revealing themselves may avoid broadcasting signals that others could detect. On Earth, humans are just beginning to consider the risks of sending messages into space. The universe may contain civilizations far more cautious, carefully managing their energy output and shielding their activity. Their choices could render entire regions of space observationally empty. In this sense, the universe's vastness and our observational limits are intertwined with behavior. The quiet we experience may reflect strategic caution, not absence. The rarity of observation reminds us of the patience required in astronomy. Searching for life is not like observing a weather pattern or studying a local ecosystem. Light years of distance, millennia of travel time for signals, and the faintness of energy emissions all combine to make detection slow and uncertain. Even repeated scans of the same stars may yield no result if civilizations remain quiet or signals are intermittent. The act of searching becomes a careful, long-term endeavor, requiring both persistence and humility. Each planet examined and each signal analyzed is part of a larger effort to understand a universe that is patient and vast beyond measure. Finally, the vast scale and rarity of observation underscore the plausibility of the dark forest theory. Civilizations that are quiet may survive longer. Those that broadcast signals might attract unwanted attention. Even if life is common, the universe could appear silent simply because intelligent beings have learned to remain hidden. Observation is limited not only by distance, time, and technology, but also by the deliberate choices of civilizations that wish to avoid detection. The cosmos, immense and full of possibilities, Maybe a quiet forest in which every life form moves cautiously, aware that visibility can be dangerous. The scale of the universe makes silence the most natural state, a condition shaped by distance, risk, and the need to survive. The Fermi paradox begins with a simple question. If the universe is so big and old, why have we never met anyone else? Enrico Fermi, a physicist, asked this during a casual conversation, but the question remains profound. The universe contains billions of galaxies, each filled with billions of stars. Many stars host planets, and many planets may be suitable for life. Probability alone suggests that intelligent civilizations should exist somewhere, yet the sky is silent. This contradiction between high likelihood and lack of evidence defines the paradox. It is a puzzle that guides much of the search for extraterrestrial life. Scientists have proposed many explanations for the paradox. One idea is that life itself is rare. Perhaps the conditions needed for life to emerge are so specific that Earth-like planets are uncommon. Water, a stable climate, the right chemicals and time are all necessary. Even if planets are common, the emergence of life may be exceptional. Life may start easily in some cases, but advanced intelligence could require billions of years to evolve. This timing may mean that civilizations are few and widely separated, reducing the chance of contact. Another explanation is that civilizations self-destruct. Technology can bring rapid change, but also risk. A civilization that develops energy sources, weapons, and industrial power may face ecological collapse or accidental destruction. This could limit the lifespan of civilizations to a few centuries or millennia, making overlap with other civilizations rare. Even if intelligent life arises often, survival may be difficult. The universe might host many short-lived civilizations, each appearing and vanishing quietly, leaving little trace for observers like us. Some scientists suggest that civilizations exist, but they are too far away to detect. The Milky Way is vast, and the distances between stars are enormous. Light travels fast, but even at its speed, signals take years or thousands of years to cross the galaxy. Two civilizations may exist simultaneously, but be separated by so much space that communication is impossible. Even if they try to send messages, timing may never align. The universe's scale alone may prevent contact, creating a silent galaxy despite the presence of life. The paradox also considers the possibility that civilizations are intentionally silent. The dark forest theory offers one explanation. Life may understand that revealing its location is risky. Survival in a universe with unknown neighbors may require caution. Civilizations that broadcast their presence could attract attention from unknown and potentially dangerous life. Quiet civilizations avoid detection, remaining hidden while listening carefully. In this scenario, silence is not absence. It is a strategic choice, a survival tactic written into behavior across planets and time. Historically, the search for signals began with radio waves. Humans began sending radio transmissions in the early 20th century. SETI, the search for extraterrestrial intelligence, began systematically listening to stars in the 1960s. Yet, despite decades of scanning, no confirmed artificial signals have been found. The silence has only deepened the paradox. Each null result adds weight to the question. Is life rare, civilizations short-lived, or deliberately hiding? Modern instruments continue to refine the search, extending sensitivity, bandwidth, and coverage. But the answers remain elusive. Mathematical approaches help frame the paradox. The Drake equation estimates the number of detectable civilizations by combining factors such as star formation rate, the fraction of stars with planets, the probability of life, and the lifespan of civilizations. Even with optimistic estimates, the resulting numbers suggest many civilizations could exist in the galaxy. Yet the lack of evidence conflicts with these calculations. This tension between expected abundance and observed silence is the heart of the Fermi paradox. It pushes scientists to explore not only astronomy, but biology, ecology, and sociology in a cosmic context. The paradox highlights how different factors combine to create silence. Distance, rarity, timing, and intentional concealment all play a role. Civilizations might exist in corners of the galaxy that are too remote for us to observe. Some may rise and fall before signals reach us. Others may choose stealth. This combination produces a universe that seems empty, even when it is not. It suggests that our perspective, limited by technology and space, may be incapable of seeing the full picture. What appears as emptiness may be a consequence of scale, survival, and caution. Understanding the Fermi paradox also reshapes how we think about communication. Sending messages to the stars is not simple. Civilizations may use methods we cannot detect. They might rely on forms of energy beyond radio waves or communicate in brief, infrequent bursts. Even if a message reaches another civilization, it may arrive long after its senders are gone. The paradox forces us to accept that contact is not guaranteed and may never occur, regardless of how many intelligent beings exist. The universe is large, and silence may be the natural outcome. Finally, the paradox encourages patience and careful observation. It teaches that absence of evidence is not evidence of absence. Life may exist widely, yet remain hidden due to distance, timing, or caution. The Fermi paradox frames the mystery that the dark forest theory addresses. Intelligent life may know that silence ensures survival. Civilizations may be abundant, yet invisible, each listening carefully while keeping its location secret. The paradox does not demand pessimism. Instead, it invites curiosity, measured reasoning, and a recognition of the vast and quiet complexity of the cosmos. In addition to distance and timing, the Fermi paradox raises questions about how civilizations behave once they develop technology. A planet may host intelligent life, but that life may not send signals intentionally. Some civilizations might focus on exploration, science, or survival rather than communication. They may use energy and resources for internal development, avoiding unnecessary exposure. In this case, the galaxy could be filled with life that is active and advanced, yet entirely hidden from our instruments. Our assumption that intelligent life seeks to communicate may be biased by human behavior, not universal patterns. Civilizations may also face natural limits that prevent their signals from traveling far. Interstellar space is filled with dust, gas, and cosmic radiation that can scatter or absorb energy. Signals weaken over distance, eventually blending into the background noise of the universe. Even if a civilization emits powerful radio waves or light signals, the strength may be insufficient to reach distant observers. The combination of distance, signal decay, and natural interference creates an environment in which life can exist, flourish, and yet remain completely undetected. Silence may be the result of physics as much as strategy. Another consideration is the lifespan of technology itself. A civilization may develop the ability to communicate across space for only a brief period before changing methods. Just as humans once broadcast wideband radio and now shift to digital, more efficient forms of communication, extraterrestrial civilizations may limit or alter their transmissions. Their early signals could fade or never reach us, and their newer technologies may be undetectable by instruments designed for older methods. This makes it challenging for astronomers to match the timing and frequency of transmissions with our own observing capabilities. The paradox also challenges the idea that civilizations must expand outward. Humans imagine space colonization as a goal, but advanced civilizations may prioritize sustainability over growth. They might focus on resource management, planetary preservation, or technological refinement instead of spreading widely. Without expansion into the galaxy, their presence remains localized and difficult to detect. Even if life is abundant, it may be concentrated in small pockets that are effectively invisible. The universe's apparent emptiness may reflect the choices intelligent species make in response to risk, resources, and survival, rather than the absence of life. Some explanations involve extreme caution or survival strategies. Civilizations that understand the potential threats from unknown neighbors may actively avoid detection. The dark forest theory suggests that intelligent life may interpret silence as safety. A civilization broadcasting its presence could be noticed by another that views it as a threat. Even if aggression is unlikely, the risk of unknown intentions might be too high. Silence becomes a rational strategy, a product of evolution on a galactic scale. In this view, the Fermi paradox is not a failure of observation, but evidence of cautious behavior among intelligent life. Mathematical models illustrate these ideas. Researchers calculate probabilities for the number of civilizations, their lifespans, and the likelihood of overlap in space and time. Even with optimistic numbers, contact may be improbable. Factors such as slow expansion, limited broadcasting, or deliberate concealment reduce the chance of detection. The paradox emphasizes that abundance does not equal accessibility. Life may thrive in ways we cannot easily perceive, leaving vast areas of the galaxy seemingly empty. Silence becomes a feature of scale, risk, and strategy combined. Even natural disasters contribute to the silence. Civilizations may face asteroid impacts, gamma-ray bursts, or supernovae that disrupt development. Catastrophic events could limit the duration of observable activity, preventing signals from traveling far. A planet may host life for millions of years, but only briefly develop detectable technology. Signals that once existed may no longer propagate, and those that are emerging now have not yet reached us. The Fermi paradox reflects both the fragility of life and the difficulties of maintaining detectable activity over cosmic time. The paradox also raises questions about behavior in social and biological contexts. On Earth, species that signal loudly often attract predators. Intelligence can increase survival, but it can also create vulnerability. Civilizations that recognize these risks may prioritize concealment. Technological activity may be subtle, signals carefully managed, and energy use intentionally hidden. In this way, the paradox connects astronomy to principles of biology and evolution. Life everywhere may act similarly, understanding that visibility can be dangerous. Finally, the Fermi paradox underscores the challenge of interpreting the silence. The absence of observed civilizations does not prove absence of life. Instead, it may reflect limitations in our instruments, our understanding, or the choices of other civilizations. The universe could be full of life, yet we remain unaware. The paradox and the dark forest theory together suggest that intelligent life may act with caution, moving quietly through the cosmos, listening while remaining hidden. The silence we perceive is consistent with the strategies required for survival in an uncertain, vast, and potentially risky universe. The idea of the dark forest theory began as a thought experiment about survival in a universe full of unknown civilizations. Scientists and even writers considered what might happen if intelligent life discovered one another across the stars. The theory suggests that life may remain silent because revealing itself can be dangerous. Just as animals hide in forests to avoid predators, civilizations in space may hide to avoid detection. The universe, vast and uncertain, may favor those who are quiet and careful. In the forest analogy, every civilization is like a hunter or prey moving quietly among others. If one reveals its position, it may invite aggression from others. The risk is not limited to hostile intent. Simply being known could make a civilization vulnerable. Survival may depend on remaining invisible. The idea connects to basic principles of biology and evolution. Species that signal too loudly often face higher risk of predation. Intelligence may enhance survival, but it also increases the consequences of being seen. In space, this effect is multiplied by distance, unknown threats, and the potential scale of damage. The dark forest theory gained attention because it offers a logical solution to the Fermi paradox. Silence may not be a failure to communicate, but a strategy. Civilizations may understand that even if most neighbors are peaceful, the universe is unpredictable. A single aggressive civilization could pose an existential threat. Acting cautiously, avoiding detection, and observing quietly may be the best approach for survival. In this sense, the silence observed across the stars could reflect deliberate choice rather than absence. Game theory provides insight into this reasoning. When multiple agents interact with uncertainty, strategies often favor caution. Even if all parties prefer peace, the possibility of a single threat can change behavior. Avoiding exposure and minimizing signals becomes rational. Civilizations may calculate that revealing information about themselves increases risk. Across billions of light years with countless unknown neighbors, the safest action is often to remain hidden. The dark forest theory frames this behavior on a cosmic scale. The analogy also draws on examples from Earth. Animals that live in large forests often rely on camouflage, quiet movement, and keen observation. Prey species learn to avoid predators, while predators remain stealthy to improve hunting success. Over time, cautious behavior is rewarded. In a similar way, civilizations that remain hidden may survive longer, while those that are loud or careless may face threats they cannot predict. The universe becomes a forest in which visibility and caution are linked to survival. The theory does not assume malicious intent by default. A civilization could be peaceful, curious, or entirely uninterested in expansion. Yet, because intentions of other civilizations are unknowable, even a peaceful society may take precautionary measures. Silence, in this view, is rational prudence. Broadcasting signals or signaling presence could be equivalent to leaving a door open in a dangerous neighborhood. The dark forest theory combines probability, logic, and evolutionary principles to suggest why civilizations may choose the quiet path. This idea also influences thinking about communication strategies. Some scientists argue that deliberately sending messages to unknown civilizations carries risks. If life elsewhere follows similar logic, an open signal could attract attention from civilizations that act differently than expected. Silence becomes a protective measure, not just a passive state. Civilizations may focus on passive observation, gathering information while minimizing exposure. This perspective reframes the search for extraterrestrial life. Rather than expecting signals, we may need to listen carefully and interpret subtle hints. The emergence of the dark forest theory also aligns with observational limitations. Even if life exists, most activity would remain hidden due to distance, natural interference, and deliberate shielding. Civilizations that practice stealth may emit energy at levels too low for detection or use wavelengths we cannot yet measure. The combination of distance, technology, and caution results in a universe that appears quiet. What seems like emptiness may actually be filled with life that chooses not to be seen, observing and surviving across vast distances. Finally, the dark forest theory emphasizes caution, patience, and perspective. It suggests that intelligent life may survive by understanding the risks inherent in a universe with unknown neighbors. The theory provides a plausible explanation for the Fermi paradox and challenges assumptions about communication, expansion, and visibility. Civilizations may exist in great numbers, yet we perceive silence. The forest is dark because life has learned that visibility can be dangerous, and the quiet observed across the cosmos may be the product of billions of years of cautious survival strategies. The dark forest theory also considers the differences in development among civilizations. Not all societies advance at the same pace. Some may remain in early technological stages for thousands of years, while others may achieve advanced technology rapidly. This disparity increases the risk for younger civilizations. A newly advanced society that signals its existence could be noticed by older, more technologically capable civilizations. The older civilizations might not be hostile, but the imbalance in power could make the younger civilization vulnerable. Silence, therefore, is not only a matter of survival, but also of understanding one's place in a complex universe. Another factor is the unpredictability of other civilizations. Even if most are peaceful, there is no way to know for certain. A civilization may follow different priorities or have values completely unlike our own. Distance magnifies this uncertainty. By the time a signal reaches another civilization, the sender's situation may have changed entirely. Plans that seemed safe at the time of transmission could become risky by the time they are received. In this context, remaining quiet is a rational choice. The dark forest theory frames the universe as a place where uncertainty itself can drive behavior toward concealment. The theory also considers resource management and environmental limits. Civilizations that expand rapidly may overuse resources, drawing attention and risking conflict with others. By contrast, societies that focus on careful, efficient management may have less reason to broadcast their presence. Energy use, infrastructure, and communication can all leave detectable traces. Civilizations that minimize these traces remain largely invisible. Over time, natural selection on a cosmic scale may favor societies that survive quietly, using minimal energy and revealing nothing beyond necessity. Visibility can be as much a liability as a tool. Civilizations may also use deliberate camouflage techniques. A technologically advanced society could mask its heat signature, redirect energy emissions, or emit signals that blend into the cosmic background. These strategies would make detection extraordinarily difficult. Even civilizations that are visible in principle may appear silent in practice. The dark forest theory assumes that such techniques are likely because survival incentives favor them. Silence is not passive. It may be an active, careful, and sophisticated strategy designed to avoid attracting attention in a universe filled with unknown neighbors. The analogy of the forest extends further. Just as animals rely on multiple senses, sight, hearing, smell, to detect threats, civilizations may observe the cosmos in complex ways while remaining hidden. They may monitor for unusual signals, energy emissions, or changes in planetary environments. Listening quietly while minimizing their own detectability allows them to assess risk without drawing notice. In a universe of countless worlds, this observational patience could be essential. Civilizations may endure for millions of years precisely because they move cautiously, avoiding visibility and observing the patterns of others without interference. History on Earth offers a parallel in strategic caution. Societies have often survived not by expansion or conquest, but by adapting to risk, avoiding conflict, and managing information carefully. Intelligence increases both capability and vulnerability. Those who reveal too much too soon risk attack or exploitation. Similarly, in the universe, the dark forest theory suggests that caution and discretion are universal survival traits. Life that signals without care may invite danger, while life that observes silently may persist. Silence becomes an adaptive strategy repeated across planets, environments, and civilizations. The theory also provides insight into why we may not have received signals yet. Civilizations may broadcast only when conditions are safe, or only in limited directions, or in formats we cannot detect. They might use wavelengths outside our current technology, or intermittent bursts that we are unlikely to catch. Even with hundreds of years of observation from Earth, our chances of intercepting an intentional or accidental signal are extremely small. The dark forest theory explains that silence may not be absence of life, but deliberate choices made by civilizations concerned with survival over communication. The idea emphasizes perspective and patience. Civilizations may operate on timescales far longer than human history. Their observation, decision-making, and communication may occur over millennia or longer. A civilization may assess risk before transmitting and wait until the environment is stable or until they judge it safe. From our point of view, this delay makes the universe appear quiet. The dark forest theory encourages understanding that the silence is not random. It is structured by strategy, risk assessment, and the realities of interstellar scale, combining distance, timing, and the unknown behavior of others. Finally, the theory encourages careful thought about humanity's own actions. Sending signals into space, broadcasting our location, or attempting communication with unknown civilizations may carry unknown risks. The lessons of the dark forest theory suggest that caution is wise, that silence can be protective, and that survival in the universe may depend on discretion. Civilizations may exist in numbers far beyond our ability to detect, but the forest remains dark because life has learned, through survival and observation, that visibility can be dangerous. The silence that stretches across space may be the universe's most enduring strategy. Detectability is at the core of our search for life beyond Earth. A civilization's presence becomes meaningful only when it can be observed or measured from afar. Scientists have long considered the signs that intelligent life might leave, known as technosignatures. These include any detectable evidence of technology, energy use, or infrastructure that could not arise naturally. For example, radio waves, laser pulses, or unusual heat emissions might suggest advanced activity. The challenge is that the universe is vast, signals weaken with distance, and detection requires instruments both sensitive and precisely tuned. Radio waves are the most familiar type of technosignature. Humans began broadcasting radio signals more than a century ago. Our signals travel at the speed of light and spread into space, forming a growing bubble around Earth. Beyond a few dozen light years, these signals fade into background noise. If a distant civilization attempted to detect us, they would need highly sensitive equipment, precise tuning, and a stroke of luck. The same limits apply to our search for others. Radio signals weaken as they travel, and only those intentionally broadcast or unusually strong might be noticeable. Even then, natural cosmic phenomena can drown out artificial signals. Other types of technosignatures include energy use, detectable as heat. Advanced civilizations might produce large amounts of waste heat as a byproduct of energy-intensive activities. This heat could be detectable across interstellar distances. Scientists have hypothesized that massive energy structures, such as Dyson spheres or swarms built around stars to capture energy, would emit infrared radiation distinguishable from natural processes. Detecting these signatures requires careful observation and a deep understanding of how natural cosmic systems behave so that anomalies can be interpreted accurately. Planetary atmospheres provide another window for detection. Chemical compositions of exoplanets can be analyzed through spectroscopy, measuring light that passes through or reflects off the atmosphere. Certain molecules, such as oxygen, ozone, methane, or combinations that are unstable under natural processes, might indicate biological or technological activity. Even traces of pollutants or artificial compounds could suggest industrial processes. The challenge is that these signals are faint, require repeated measurements, and can be masked by natural atmospheric variations. Detecting technosignatures is not simply about finding life, but discerning the artificial from the natural. Light itself can also be a technosignature. Civilizations may use lasers or other directed energy emissions for communication or energy transmission. High-intensity, narrow-band signals could be distinguishable from stars or natural sources if aimed in our direction. Searching for these signals requires precise instruments and continuous observation. A civilization broadcasting for only brief periods or intermittently may never be detected, and even civilizations that are constantly active may appear silent unless we happen to be in the right place at the right time. Detection is limited not only by technology, but also by geometry and timing. Stealth and concealment further complicate detectability. A civilization that understands the risks of revealing its presence may limit emissions. It may shield or redirect energy to avoid unwanted observation. Even planetary heat, light, or radio emissions could be managed to blend into the background. This intentional discretion aligns with the dark forest theory. Survival may require avoiding detection. Civilizations may exist across the galaxy, but their strategies for remaining hidden render them effectively invisible. The universe might be teeming with intelligent life that we simply cannot perceive. The rarity of detection is also influenced by scale and distance. Stars are separated by light years, and signals weaken according to the inverse square law. Energy spreads over an ever-growing sphere. A broadcast strong enough to be detected nearby may be imperceptible across a few hundred light years. Observational technology must therefore be exceptionally sensitive. Radio arrays, space telescopes, and spectroscopy instruments extend our reach, but the signals of intelligent life may still fall below our thresholds. Even if life is common, the limits of physics create natural silence. Timing is crucial. Civilizations may only be detectable during brief technological phases. Humans, for example, have emitted radio waves for slightly more than a century. Future technology may become more efficient, emitting less energy, or communication may shift to forms we cannot yet detect. A civilization's detectable window may last only a few hundred years, or a few thousand at most, short on cosmic timescales. Over millions or billions of years, the probability that two civilizations overlap within detectable range becomes extremely small. Silence may thus result from both strategy and the brief observable lifetimes of civilizations. Humanity's current search focuses on multiple technosignature types simultaneously. Radio telescopes, such as the Allen Telescope Array, scan thousands of stars, searching for narrow-band or repeating signals. Optical observatories search for pulses of light, unusual spectral lines, or megastructures. Infrared surveys look for excess heat from stars that might indicate massive energy harvesting projects. Even gravitational effects, such as unusual orbital patterns, could hint at large-scale engineering. Each method addresses a different possible signal, yet all face the challenge that the universe is vast, signals are faint, and intentional concealment may be widespread. Observational noise presents additional challenges. Stars fluctuate in brightness, cosmic dust scatters radiation, and energetic events create bursts of energy that mimic artificial signals. Separating natural phenomena from potential technosignatures requires sophisticated data analysis, statistical models, and repeated observations. A signal that seems unusual may turn out to be a natural process once examined carefully. This uncertainty reinforces the idea that the universe can appear empty even when advanced civilizations exist. Signals may exist, but we may be unable to recognize them. Civilizations may also use forms of communication we cannot yet imagine. Electromagnetic waves are familiar to humans, but other methods, such as neutrinos, gravitational waves, or quantum-based signals, may be beyond our current detection capability. A society capable of manipulating such phenomena could communicate across the galaxy while leaving no detectable trace for our instruments. Stealth may be a natural outcome of advanced technology. Civilizations may evolve methods of signaling that are efficient for themselves but invisible to others. The universe may be full of life that is undetectable by design. Energy efficiency is another factor in detectability. Civilizations that optimize their energy use will naturally emit less waste heat, light, or radio energy. Even industrialized societies may produce minimal detectable signals if they focus on low-energy technologies. Energy conservation becomes a strategy not only for sustainability, but also for invisibility. The dark forest theory aligns with this principle, suggesting that advanced civilizations may hide not only from risk, but also by design, intentionally blending into the cosmic background to survive across vast timescales. Detection also depends on civilization behavior. Some may focus on exploration, building infrastructure on their own planets or solar systems rather than broadcasting outward. Others may explore silently, sending automated probes or observing from a distance. The choice to remain non-communicative could be widespread. Across the galaxy, civilizations that avoid signaling may outlast those that broadcast indiscriminately. Survival strategies favor discretion, making detectability a function of both physics and sociology. Silence is therefore a feature of risk management and evolutionary advantage. Finally, the search for technosignatures teaches humility. Even with powerful instruments and decades of observation, we may see only a fraction of what exists. Life may thrive in many forms, yet remain invisible because of distance, timing, energy efficiency, or deliberate stealth. The dark forest theory suggests that silence is often the rational choice. Detectability is limited not only by our technology, but also by the strategies of those we hope to observe. The universe may be full of intelligent civilizations, yet quiet because survival has taught them discretion. Our challenge is to listen patiently, observe carefully, and understand that silence may conceal a forest of activity beyond our perception. The idea of contact in the universe carries risks that are often overlooked. Signaling to other civilizations might seem harmless, yet even simple exposure can have consequences. In the context of the dark forest theory, visibility may attract attention from unknown and potentially dangerous life. Civilizations that signal their location are, in effect, announcing themselves in a vast, unpredictable environment. The analogy to predation on Earth helps illustrate the danger. Just as animals risk being hunted by signaling or moving too openly, civilizations may invite harm by revealing their presence to unknown neighbors. The stakes are far higher in interstellar terms, because the potential for damage is enormous and the intentions of others are unknowable. Resources in the universe are not evenly distributed. A planet or solar system with abundant energy, minerals, or habitable conditions may be highly valuable to other civilizations. If a civilization signals its location, it could attract attention from societies that seek to expand or exploit resources. Even if aggression is unlikely, the mere possibility of competition creates incentive for caution. The balance between visibility and safety becomes a central concern. A civilization may weigh the benefits of communication against the risk of drawing attention from potentially hostile or opportunistic neighbors. In a vast and uncertain galaxy, survival often outweighs curiosity. Historical examples on Earth demonstrate the consequences of first contact between civilizations. When technologically advanced societies encountered less advanced groups, the results were often disastrous for the less powerful. Entire populations could be destroyed or subjugated due to superior weaponry, strategy, or knowledge. These events are not directly analogous to interstellar encounters, but they illustrate a principle that may apply universally. Disparities in technology and knowledge create risk. A newly advanced civilization broadcasting its presence could encounter others far older, more capable, and potentially dangerous. Silence becomes a protective measure learned from these lessons of history, scaled to cosmic proportions. Probability plays a significant role in understanding risk. Even if most civilizations are peaceful, the likelihood that a small fraction could be aggressive has consequences. If a single aggressive civilization exists within communication range, any visible civilization could be at risk. Rational actors in a dangerous environment may assume the worst, choosing caution over trust. The universe may favor societies that remain hidden and minimize detectable activity. From a statistical perspective, the benefits of signaling are uncertain, while the potential costs are catastrophic. Risk management on a galactic scale suggests that caution is often the safest strategy. Distance and time further complicate the calculation of risk. Signals travel at the speed of light, and civilizations may exist thousands of light years apart. By the time a signal is received, the conditions of both civilizations may have changed. The sender may have evolved, collapsed, or disappeared, and the receiver may have developed technology or motives different from what the sender anticipated. This temporal lag introduces uncertainty, making exposure inherently risky. A civilization cannot predict the responses of others accurately, so minimizing detectable emissions becomes a rational strategy, reducing the chance of unintended consequences over cosmic timescales. The potential scale of conflict is vast. Interstellar civilizations may possess energy and technology far beyond our understanding. The consequences of aggression are therefore enormous. Even minor misinterpretations of signals or intentions could escalate into catastrophic outcomes. A civilization that reveals itself unnecessarily could trigger responses that threaten its survival. The stakes are orders of magnitude higher than any historical human encounter. The dark forest theory reflects this reality. In a universe of unknown neighbors, the safest choice is often silence, because visibility may invite danger that cannot be mitigated once observed. Expansion itself carries risk. Civilizations that attempt to colonize or explore widely may leave traces of energy or signals that reveal their location. Each expansion increases exposure and the possibility of encountering other societies. Resource competition, territorial disputes, and technological disparities could all result in conflict. A civilization seeking survival may therefore limit expansion, focus on energy efficiency, and minimize detectable activity. In this context, risk management is inseparable from strategic discretion. Civilizations may endure longer by prioritizing invisibility over exploration, using minimal signals, and observing quietly. Technological asymmetry is another concern. A younger or less advanced civilization may underestimate the abilities of others. Even if a neighbor appears benign, the unknown factor of superior technology introduces risk. An aggressive or highly capable civilization could exploit any weakness, intentionally or accidentally causing harm. This possibility reinforces the rationale for remaining hidden. Advanced societies may remain quiet, not only to avoid detection, but also to prevent revealing vulnerabilities. Cosmic prudence suggests that exposure can be more dangerous than non-communication, regardless of intent. Observational limits of other civilizations also play a role. While we may struggle to detect life, other societies may have far more sensitive instruments, capable of observing subtle signals or energy patterns. A civilization unaware of its detectability may inadvertently reveal itself to more capable observers. The asymmetric risk is significant. The less advanced or less cautious party is at disadvantage. This encourages discretion and careful management of energy emissions, communication, and exploration. In essence, the universe rewards those who remain silent while punishing those who broadcast indiscriminately. Even civilizations focused on peace or scientific study face risk. A message intended as greeting, exploration, or knowledge sharing could be misinterpreted by others. Intentions are unknowable across vast distances and cultures. The possibility of misunderstanding adds another layer of danger. Silence acts as a protective buffer against miscommunication and unintended consequences. The dark forest theory proposes that the combination of unknown intentions, technological disparity, and potential aggression creates a natural incentive for discretion, where survival often depends on remaining unseen. Probability analysis further suggests that aggressive civilizations, even if rare, dominate risk calculations. If 1% of civilizations are aggressive and 99% peaceful, any visible society faces a 1% chance of catastrophic encounter. The cost of failure is existential, while the benefit of communication may be uncertain or delayed by thousands of years. From an evolutionary standpoint, societies that avoid detection, manage risk carefully, and minimize exposure are more likely to survive. This statistical logic may govern behavior across the galaxy, shaping the overall silence we observe. Historical analogies reinforce this reasoning. On Earth, early encounters between human civilizations often resulted in devastating consequences for the less technologically developed society. In space, technological disparities are amplified, and survival stakes are higher. Civilizations broadcasting signals may expose themselves to threats that cannot be fully anticipated. Even well-intentioned contact carries risk. Silence becomes not only a strategy, but an adaptive necessity, ensuring that civilizations avoid unnecessary exposure until they can better assess the environment. The dark forest. Theory and risk of contact also consider cumulative effects. Each signal, exploration mission, or energy emission adds to the probability of detection. A civilization that accumulates exposure over time increases its risk. By limiting signals, reducing energy waste, and remaining stealthy, civilizations minimize cumulative risk. Patience and long-term planning become essential. Survival may depend on a slow, careful strategy, prioritizing observation over communication, and considering consequences across centuries or millennia. Finally, the universe may favor those who stay quiet. Civilizations that avoid detection, manage resources, and carefully calculate risk may persist for far longer than those that broadcast recklessly. Aggression may be rare, but the catastrophic potential makes even a small probability significant. Silence, discretion, and careful observation are rational strategies for survival. The dark forest theory frames these strategies as natural outcomes of life in a universe of unknown neighbors, vast distances, and enormous stakes. The quiet of the cosmos may reflect an immense, deliberate effort by civilizations to survive rather than a lack of life. The emergence of life in the universe is not guaranteed. While stars and planets are abundant, the conditions required for life are specific. A planet must have the right temperature, chemical composition, liquid water, and atmospheric stability. These factors together create a narrow window of habitability. Even small deviations in planetary conditions can prevent life from forming or persisting. Life on Earth emerged under a unique combination of factors, including a stable climate, a protective magnetic field, and the presence of essential elements. These conditions are rare, making life itself a precious and delicate phenomenon. Planetary conditions are dynamic over time. Geological activity, climate cycles, and orbital changes influence habitability. A planet may be suitable for life for only a fraction of its existence. Events such as asteroid impacts, supernova radiation, or shifts in atmospheric composition can extinguish life or dramatically alter evolutionary pathways. Civilizations, if they arise, must survive these natural challenges. The universe is not static. It changes on timescales that may exceed the lifespans of individual civilizations. Longevity depends on adaptability, resilience, and timing, factors that are difficult to predict and observe from afar. The Drake equation attempts to quantify the number of civilizations in the galaxy. It combines variables such as the rate of star formation, the fraction of stars with planets, the fraction of planets that develop life, the fraction of life that becomes intelligent, and the lifespan of technological civilizations. Each factor is uncertain, yet together they provide a framework for thinking about cosmic life. Even optimistic assumptions produce results that suggest civilizations may exist, yet remain undetected due to rarity, timing, or short lifespans. Refinements to the equation increasingly emphasize survival challenges, the brevity of technological windows, and the rarity of stable, habitable environments. Extinction events play a crucial role in limiting the persistence of life. On Earth, mass extinctions have wiped out large portions of species multiple times. Life has persisted, but the conditions for intelligent civilizations are far more delicate. A single global catastrophe, whether geological, astronomical, or ecological, could end a civilization. Even minor disruptions can slow technological development, reduce population, or limit resource availability. Longevity is therefore a combination of planetary stability and the ability of intelligent life to adapt to changing conditions. The longer a civilization survives, the more likely it is to become detectable, yet these conditions are rare. Civilizations face technological risks as well. Advanced energy systems, industrial processes, and large-scale projects carry the potential for accidents. Nuclear energy, artificial intelligence, and ecological manipulation can provide tremendous benefits, but also pose existential threats. A civilization must manage these risks carefully to persist. The brevity of detectable signals may reflect both natural fragility and technological vulnerability. Many civilizations may rise and vanish before their presence can be observed. The universe may appear silent, not because life is absent, but because survival is difficult and visibility is brief. Societal factors also affect longevity. Cooperation, stability, and effective governance influence how civilizations respond to challenges. Internal conflict, resource mismanagement, or social collapse can limit the lifespan of a civilization. Even technologically capable societies may fail to survive if societal structures are weak or adaptability is low. Longevity depends on multiple layers: planetary conditions, technological management, and social cohesion. A failure in any layer can shorten the window of detectability, making advanced life less likely to be observed across interstellar distances. Short-lived civilizations, though potentially abundant, reduce detectability. If most civilizations last only a few centuries or millennia before collapse, the overlap with other civilizations becomes minimal. Even if life is widespread, the probability of two societies existing simultaneously within detectable range is small. Signals may be emitted briefly, only to fade before reaching other observers. The universe may host countless brief flares of activity that never intersect. The silence we observe may reflect a combination of rarity, brief technological lifespans, and the vast distances separating civilizations. Life's emergence is also constrained by chemical and environmental factors. The presence of carbon, nitrogen, oxygen, and other elements is essential for complex molecules. Planetary conditions must allow stable chemistry over millions of years. Energy sources, such as sunlight or geothermal heat, must be sufficient and consistent. A small variation in these parameters can prevent life from forming or persisting. Even when conditions are favorable, evolution toward intelligence is not guaranteed. Many worlds may host simple life forms, but only a tiny fraction produce complex, intelligent life capable of broadcasting or building technology. The probability of observing life is further influenced by the rarity of long-term stable environments. Many planets may experience cycles of habitability, with periods too short to allow the evolution of complex life. Stellar behavior, orbital instabilities, and planetary catastrophes contribute to this instability. Civilization development requires long periods of environmental stability. Short-lived habitable windows make the evolution of intelligent life less likely. Even if life emerges, survival long enough to develop technology may be rare, explaining why the cosmos appears quiet despite potentially many habitable worlds. Cumulative risk must also be considered. Each layer of survival, planetary, biological, technological, and societal, carries the potential for failure. The probability of a civilization surviving each successive challenge may be low. Multiplying these probabilities produces an even smaller chance that a civilization persists long enough to be detectable. This perspective emphasizes why the Fermi paradox exists. Life may arise more often than we observe, but survival to technological maturity and sustained visibility is rare. The combination of emergence, longevity, and detectability forms a bottleneck that shapes the apparent silence of the galaxy. Recent refinements of the Drake equation take these factors into account. Scientists now consider short-lived civilizations, intermittent technological phases, and the possibility that advanced life intentionally minimizes detectability. These adjustments reduce expected numbers of observable civilizations while preserving the possibility of widespread life. The universe may contain numerous forms of life and intelligence, yet the combination of rarity, extinction events, and brief windows of detectability produces the quiet we observe. Life may flourish, but its visibility is restricted. Finally, longevity ties directly to the dark forest theory. Civilizations that survive for long periods may do so by remaining hidden, conserving energy, and managing risk. Their long-term persistence depends on avoiding detection by potentially aggressive neighbors, limiting visible signals, and adapting to both natural and self-imposed challenges. Short-lived civilizations, by contrast, are more likely to disappear before they can be observed. The rarity and fragility of life, combined with strategic discretion, provide a plausible explanation for the paradoxical silence of the universe. Life exists, but its survival and visibility are constrained by both cosmic and strategic factors. The search for life beyond Earth is grounded in observation. Astronomers have identified thousands of exoplanets, many of which orbit within their star's habitable zone, where temperatures could allow liquid water. The habitable zone, often called the Goldilocks zone, is not too hot and not too cold. It is a region where planetary conditions may support life as we know it. By studying these exoplanets, scientists can determine factors such as size, orbit, and stellar energy, which inform the probability of habitability. Observations are conducted using methods like transit photometry, where a planet passing in front of its star slightly dims the starlight, and radial velocity measurements, which detect the gravitational influence of a planet on its star. Once a potentially habitable planet is found, its atmosphere becomes a primary focus. Atmospheric composition can reveal the presence of water vapor, oxygen, methane, carbon dioxide, and other chemicals associated with life. Spectroscopy, the study of light absorption and emission, allows astronomers to infer these components. Different molecules absorb light at specific wavelengths, creating identifiable patterns. By analyzing starlight that passes through a planet's atmosphere, scientists can detect these patterns, even at great distances. Variations in these signals may indicate dynamic processes, potentially caused by biological or technological activity. Biosignatures are among the most promising indicators of life. They include chemical imbalances or compounds that would not persist naturally without ongoing replenishment. Oxygen is a prime example, as it reacts quickly with other elements and must be continuously produced by biological processes to remain in an atmosphere. Methane can also be a biosignature, especially when found with oxygen, because the two gases react chemically. Detecting these compounds together increases the likelihood that life is present. However, interpreting biosignatures requires caution, as some chemical processes can be non-biological. Understanding the planetary context is essential for accurate conclusions. Technosignatures complement biosignatures by focusing on evidence of technology rather than biology alone. This includes electromagnetic emissions, unusual heat patterns, artificial illumination, or signs of large-scale structures. Searches for technosignatures often involve radio telescopes, optical observations, and infrared surveys. Researchers look for narrow-band signals, repeated pulses, or patterns unlikely to arise naturally. The search is challenging because the signals may be intermittent, weak, or directed away from Earth. Observational strategies must account for these limitations, requiring careful monitoring, analysis, and interpretation of massive amounts of data. Despite decades of searching, results remain largely null. No confirmed technosignature has been detected, and biosignature evidence is still inconclusive. This absence is scientifically significant. Null results help refine estimates of life's abundance, improve observational strategies, and guide future research priorities. Scientists consider the limits of current instrumentation, the distances involved, and the brief windows during which life may be detectable. Silence does not prove absence. Rather, it informs probability assessments and helps shape the understanding of what is realistically observable given current technology. Advances in telescopes and instruments are expanding observational capabilities. The James Webb Space Telescope, JWST, launched recently, can analyze exoplanet atmospheres with unprecedented sensitivity. By observing in the infrared, JWST can detect heat signatures, molecular composition, and temperature variations. Future ground-based observatories, such as the Extremely Large Telescope, ELT, will have enormous collecting area and adaptive optics to correct for atmospheric distortion. These instruments increase the potential to identify both biosignatures and technosignatures, allowing scientists to detect weaker signals and analyze smaller planets farther from Earth. Techniques are constantly improving. High-resolution spectroscopy transit timing variations, and direct imaging provide complementary ways to study exoplanets. Each method offers unique advantages. For instance, direct imaging allows the detection of reflected starlight or thermal emissions, while spectroscopy reveals chemical composition. Combining multiple methods increases confidence in identifying habitable conditions or life-related activity. Observational science is iterative. Null results refine. Techniques suggest new targets and improve sensitivity. Every observation, even without detection, contributes to a better understanding of where life could exist. Observational data also informs models of planetary habitability. By studying known exoplanets, scientists can identify patterns such as the relationship between stellar type and planet size, orbital distance, or atmospheric composition. These patterns inform the probability that other worlds may support life. Habitability models integrate physics, chemistry, geology, and climatology to create simulations of potential planetary environments. Observational evidence validates or challenges these models, helping refine expectations for life's distribution in the galaxy. Each confirmed measurement adds a small piece to a vast cosmic puzzle. Researchers also study solar system bodies as analogues. Mars, Europa, Enceladus, and Titan provide insights into habitability under different conditions. Water ice, subsurface oceans, and chemical activity indicate that life could exist in diverse environments. Studying these bodies improves understanding of the limits and adaptability of life, which in turn informs searches for exoplanets. Observations of our own solar system complement distant studies, providing ground truth for models and helping interpret signals from faraway worlds. Null results in searches for extraterrestrial life highlight the importance of patience. Observational efforts are still relatively recent on a cosmic scale. Even with advanced instruments, the sheer size of the galaxy and the finite sensitivity of detectors make finding life extremely challenging. Researchers emphasize that the absence of detected signals does not indicate absence of life. Instead, it underscores the rarity, subtlety, and possible intentional concealment of civilizations. The dark forest theory provides one explanation for why signals might be hidden despite the presence of life. Collaborative projects enhance detection capabilities. International efforts, such as the Breakthrough Listen initiative, coordinate large-scale surveys for radio signals from nearby stars. Combining resources, observation time, and expertise allows wider coverage and higher sensitivity. Similarly, space missions designed to characterize exoplanets, like TESS and Plato, provide critical data for identifying potential targets for more detailed analysis. These coordinated efforts increase the probability of detecting life or technological activity if it exists within observational reach. Future prospects are promising. With the JWST, ELT, and other planned observatories, scientists will observe smaller, Earth-like exoplanets with greater precision. Improvements in adaptive optics, signal processing, and data analysis enhance sensitivity. Potential biosignatures or technosignatures may become detectable within the next few decades. Null results so far serve as guides, refining expectations and helping target observations more effectively. Every data point, whether positive or null, contributes to a growing understanding of life's distribution and detectability in the universe. The study of atmospheric composition remains central. Molecules like oxygen, methane, and carbon dioxide, when detected under the right conditions, indicate potential biological activity. Scientists must account for natural sources, chemical reactions, and planetary context to avoid false positives. Advanced modeling helps distinguish artificial or biological processes from natural phenomena. Observational accuracy depends on repeated measurements, multiple instruments, and careful calibration. The combination of spectroscopy, photometry, and thermal observation forms a comprehensive toolkit for searching for life. Techno-signature searches extend to unusual energy patterns. Megastructures, artificial illumination, or waste heat may produce infrared excesses distinguishable from natural processes. These signals would be subtle but detectable with sensitive instruments. Observing many star systems over time allows for identification of anomalies. By monitoring changes in brightness, spectral shifts, or unusual energy emissions, researchers can pinpoint candidates for further study. The potential for discovery increases as observation duration and sensitivity improve, highlighting the importance of continuous monitoring. Observational research continues to integrate theory and data. Models of life emergence, planetary habitability, and civilization behavior inform which targets to prioritize. Observations, in turn, refine these models, providing feedback loops that improve predictions. Null results guide adjustments in assumptions, recalibrate expectations, and shape future instrument design. The scientific process is iterative, with each discovery or non-discovery contributing to understanding. Even the absence of detected life tells a story, helping quantify probabilities and refine searches for habitable worlds and intelligent civilizations. Finally, observational evidence places the Fermi paradox and dark forest theory in context. Exoplanet discoveries, atmospheric studies, and techno-signature searches suggest that habitable conditions may be common, yet detectable life is rare. The silence of the cosmos is consistent with life being sparse, short-lived, or intentionally hidden. Advances in telescopes, instrumentation, and observation techniques promise to improve detection, but patience remains essential. The quiet observed today may conceal a universe teeming with life, activity, and civilizations practicing caution on a cosmic scale. The dark forest theory presents profound implications for humanity. If civilizations in the universe may hide to survive, then broadcasting our presence could carry unforeseen risks. Sending signals or messages into space, whether intentionally or through leakage, exposes Earth to the possibility of detection by civilizations with unknown intentions. The theory suggests that even peaceful intentions cannot guarantee safety, because intentions, capabilities, and behaviors of other civilizations are unknown. Humanity must consider these risks when deciding whether to actively communicate with extraterrestrial intelligence. Metai, or messaging to extraterrestrial intelligence, is an area of study that explores deliberate communication with potential extraterrestrial civilizations. Ethical questions arise when deciding whether to send messages. Should humanity take the initiative to broadcast our existence, or should we remain silent to ensure safety? Metai debates emphasize responsibility and caution, weighing curiosity and the desire for knowledge against survival. The dark forest theory provides a cautionary framework, suggesting that silence may be the most prudent approach until we better understand potential risks. Long-term human strategies could reflect cosmic prudence. Silence may allow humanity to observe without exposing itself. This does not imply that exploration or technological progress must halt, but rather that risk management should inform decisions about what signals are sent, what technologies are deployed, and how much of our activities are visible from space. Conserving energy, minimizing detectable emissions, and carefully monitoring interstellar signals could help ensure humanity's long-term survival. In essence, prudence on a cosmic scale becomes a guiding principle for strategy. Space exploration itself presents both opportunity and risk. Colonization of other planets or solar systems may spread humanity beyond a single world, enhancing long-term survival, but it may also increase exposure to potential threats. Expansion must be balanced with stealth and careful planning. Establishing colonies within shielded or less detectable regions, using energy-efficient systems, and minimizing visible signatures can reduce risks while still allowing human presence to expand. Risk assessment and strategic foresight become integral components of any spacefaring civilization. Ethical considerations extend beyond human safety. Decisions about sending messages or exploring distant worlds may impact future generations, both human and extraterrestrial. Messages we send could influence civilizations that encounter them millions of years later. This responsibility emphasizes long-term thinking and careful planning. Humanity must consider not only immediate outcomes, but also the distant, unforeseen consequences of revealing its existence in a universe of unknown actors. The dark forest theory highlights that survival depends on foresight and measured actions. Humanity may also learn from observation. Detecting biosignatures or technosignatures from distant planets can inform how we manage risk. If other civilizations appear to remain hidden, we can interpret this as a signal about prudent behavior. Conversely, if detectable civilizations are observed without apparent harm, it may suggest lower risk, but uncertainty always remains. Observational science provides both information and cautionary guidance, helping shape policy and strategy based on the behavior of the cosmos itself. Technological development must consider detectability. Energy-intensive activities, large-scale communication, and industrial growth all increase visibility. Humanity's technological trajectory could influence exposure risk. Conscious decisions about energy use, signal strength, and communication strategies may reduce vulnerability. For example, transmitting brief, targeted signals instead of continuous broadcasts can limit detectability. Similarly, colonization efforts can be designed to minimize infrared signatures or radio leakage. Technology, therefore, must be guided by an understanding of interstellar prudence. Cosmic timescales also influence decision-making. Civilizations operate across millions or billions of years. Human decisions today may have consequences far into the future. Long-term thinking requires patience, foresight, and scenario planning. The dark forest theory suggests that civilizations that survive tend to act cautiously, avoiding unnecessary exposure and prioritizing adaptive strategies over aggressive communication. Humanity may adopt similar principles, ensuring that our presence in the galaxy evolves with both ambition and restraint. Ethics and strategy intersect in exploration. Missions to other planets, star systems, or potential habitable worlds must weigh scientific gain against exposure. Unmanned probes, observational satellites, and carefully designed instruments can gather knowledge while limiting detectable signatures. Decisions about human travel or settlement may prioritize safety, stealth, and sustainability, integrating both ethical responsibility and survival strategy. The principle is clear. The universe rewards caution as much as capability. Education and policy play roles in long-term planning. Humanity must cultivate awareness of cosmic risks, technological limitations, and survival strategies. Decisions about METI, exploration, energy use, and observation should be informed by scientific knowledge and prudence. By preparing strategies based on the behavior of civilizations and the principles outlined in the dark forest theory, humanity increases its chances of enduring for millennia while contributing responsibly to cosmic knowledge. Science fiction often inspires exploration, but the dark forest theory encourages grounding aspirations in reality. Human curiosity is valuable, yet curiosity without caution may be risky. Active signaling, unchecked energy use, or unplanned expansion could inadvertently expose humanity. By integrating ethical, technological, and observational knowledge, we can explore the galaxy without creating unnecessary vulnerability. The philosophy of cautious progress becomes an operational guide, shaping exploration, communication, and settlement. International collaboration enhances safety. Coordinated decision-making, shared technology, and unified observation programs allow humanity to pursue exploration while minimizing risk. Collective governance over METI decisions, technological emissions, and space colonization ensures a cohesive approach to cosmic prudence. The behavior of the global human civilization becomes as important as individual technological achievements. Cooperation increases adaptability and reduces the likelihood of accidental exposure or conflict on a cosmic scale. Observation remains central to ethical and strategic planning. By studying exoplanets, monitoring signals, and analyzing the cosmos, humanity can refine expectations about life and civilization elsewhere. Each discovery or null result informs policies, risk assessment, and technological design. Patience and long-term observation allow humans to make decisions grounded in evidence rather than speculation. The dark forest theory emphasizes that understanding the universe requires both knowledge and restraint. Civilization longevity is tied to survival strategy. Technological sophistication alone does not guarantee persistence. Societies that combine innovation with careful risk management, energy efficiency, and observational patience are more likely to endure. Silence, discretion, and measured exposure may become essential survival traits. Humanity, as it matures technologically, must adopt similar strategies to ensure that progress does not inadvertently create existential vulnerability. Caution may be as vital as capability in cosmic survival. Philosophical reflection complements practical strategy. Considering our place in a universe of unknown civilizations invites humility. Humans are not the first, nor necessarily the most advanced, participants in the galaxy. Awareness of cosmic risk, rarity of life, and the potential for aggressive or capable neighbors encourages thoughtful planning. Decisions about signaling, colonization, and technological development become not just technical choices, but philosophical commitments to responsible, long-term survival. Finally, the dark forest theory provides both warning and guidance. It suggests that the universe is quiet, not because life is absent, but because survival requires discretion. Humanity can interpret this silence as advice. Observe carefully, avoid unnecessary exposure, manage energy and communication wisely, and expand strategically. Exploration, research, and technological development can continue, but tempered by prudence, foresight, and ethical responsibility. The quiet cosmos is a teacher, emphasizing that intelligence and survival may be inseparable from caution. As we consider the vast expanse of the universe, the mystery of life beyond Earth becomes both humbling and profound. The dark forest theory provides a framework for understanding why we might not yet detect other civilizations. The theory suggests that survival in a galaxy of unknown neighbors favors discretion, caution, and invisibility. Civilizations that remain quiet, manage energy efficiently, and avoid unnecessary signaling are more likely to endure. Silence is not absence, but a strategy shaped by risk, probability, and the unknowable intentions of others. The universe is unimaginably large. Hundreds of billions of stars fill each galaxy, and there are hundreds of billions of galaxies in the observable cosmos. Many of these stars host planets, some of which reside in the habitable zone where life could theoretically exist. Yet, despite the abundance of potential homes for life, we see quiet. The immense distances, light speed limitations, and faintness of signals mean that even civilizations that exist may be imperceptible. Detection is difficult, requiring patience, sensitive instruments, and often a degree of luck. The silence we observe is a natural outcome of scale and physics. Observational techniques provide us glimpses into this cosmic landscape. Telescopes like the James Webb Space Telescope, the Extremely Large Telescope, and other space-based and ground-based instruments allow us to study exoplanets in detail. We can analyze atmospheres, search for water, oxygen, methane, and other potential biosignatures. We can listen for radio waves, search for laser pulses, and monitor infrared radiation for hints of technological activity. Each observation contributes to a growing understanding, even if the signals we hope to find remain absent or inconclusive. Null results themselves carry meaning. The absence of detectable signals helps refine our models of the galaxy and the distribution of life. They indicate that either life is rare, technological civilizations are short-lived, or advanced civilizations intentionally remain undetectable. Each null detection improves our understanding of what is plausible and what remains hidden. The universe teaches patience and humility. We learn to measure probabilities, understand risk, and appreciate the limits of our perception. Silence is a teacher, urging careful observation and thoughtful interpretation. At the same time, the scale of the cosmos invites wonder. Even if civilizations remain hidden, the possibility that life exists elsewhere is enormous. The sheer number of stars, planets, and habitable worlds means that Earth may not be unique, only one among many. The universe, in all its immensity, offers space for curiosity, imagination, and hope. The quiet allows for reflection, prompting us to think about survival, intelligence, and the delicate balance between visibility and caution. It reminds us that life may flourish quietly in ways we have not yet detected or cannot yet comprehend. Humanity's role in this vast context is delicate. As observers, explorers, and potential participants in the galactic community, we face choices that affect long-term survival. Decisions about signaling, space exploration, and energy use require both scientific reasoning and philosophical reflection. The dark forest theory guides us toward prudence, suggesting that silence may be wise until we better understand the risks. Our actions today may influence outcomes millions of years into the future, emphasizing the importance of foresight and caution. Reflecting on life's rarity and fragility brings a sense of calm and perspective. Our planet is one of the few places we know of that hosts life. Civilization is young, technology is new, and our understanding of the universe is limited. Yet, within this small corner of space, humans have developed science, observation, and reasoning that allow us to explore questions about life beyond Earth. The endeavor is both remarkable and humbling. The universe is vast, mysterious, and beautiful, offering endless possibilities for discovery without requiring immediate answers. The dark forest. Theory is not meant to create fear, but to inspire thoughtful observation. Civilizations may exist, quietly hidden, each making choices to survive. Silence may be the natural default, a strategy honed by millions of years of evolution and cosmic experience. The galaxy may be teeming with life, yet hidden from view, allowing us to imagine countless forms of existence while we observe carefully and patiently. This quiet cosmos encourages reflection, patience, and appreciation for the intricate balance between curiosity and caution. Technological and observational progress continues to expand our reach. Future telescopes, probes, and instruments may reveal subtle signs of life, biosignatures, or technological activity. As humans advance scientifically, we learn to detect weaker signals and analyze more distant worlds. Each new discovery teaches us about habitability, evolution, and the strategies civilizations may use to survive. Observation becomes a dialogue between knowledge and patience, allowing us to study the universe without necessarily revealing ourselves, following the principles suggested by the dark forest theory. Space exploration, when undertaken with care, allows us to grow as a civilization while minimizing exposure. Robotic missions, orbital observatories, and carefully managed colonies provide the opportunity to learn and expand without unnecessary risk. Humanity may explore, settle, and observe while practicing discretion, energy efficiency, and technological restraint. The galaxy, in this view, becomes a classroom, laboratory, and a place of wonder, where survival is balanced with curiosity and discovery. Finally, as we look toward the stars, there is space for imagination. Even in silence, the possibility of life, intelligence, and distant civilizations fills the mind with wonder. The dark forest theory, combined with scientific reasoning and observational knowledge, frames our understanding of cosmic silence not as emptiness, but as strategic quiet. Life may be abundant, yet hidden, and the universe may contain countless civilizations that remain unseen, each practicing caution to endure over time. The vastness, quiet, and mystery of the cosmos create a reflective calm. Observing the universe encourages thoughtfulness, patience, and humility. Life is rare, civilizations may be short-lived or hidden, and detection is difficult. Yet the potential for discovery, the possibility of other intelligent beings, and the scale of the galaxy invite endless curiosity. We can watch, measure, and imagine while respecting the cosmic rules of risk, caution, and survival. As we end this reflection, it is important to feel the calm and continuity of the universe. The stars continue their silent journey, planets orbit steadily, and galaxies spin in vast, quiet elegance. Civilizations may exist unseen, life may thrive in hidden corners, and humanity can continue to observe, learn, and grow. The universe is immense, full of possibility and patient. It allows us to wonder, to explore within our limits, and to dream of life that may exist quietly beyond our reach. Even in silence, the cosmos speaks of vastness, mystery, and the potential for life, inviting gentle contemplation and quiet imagination.